Okay, in today's lecture, we're going to cover the section 5.5 material on triple integrals in terms of cylindrical or spherical coordinates. So we had seen when we were talking about double integrals for certain regions in the plane, like integrating over disks, we could, or say a cardioid-shaped region, we would make a change to polar coordinates in order to make our iterated integral easier to evaluate over that disk-shaped plane region. So the idea in this section is going to be similar. If we have some triple integral of a function of three variables, which we want to evaluate over a bounded solid region in space, well, certain regions in space are more easily described using cylindrical or spherical coordinates rather than the rectangular coordinate system. So converting our integral to an integral in terms of spherical or cylindrical coordinates will make evaluating those triple integrals much easier. So in the first part of this section, we're going to talk about evaluating triple integrals using cylindrical coordinates. So before we jump into that, let's review briefly what the cylindrical coordinates for a point in space are. So recall here, for a point in space, we can define it in terms of x, y, z, or as r, theta, z, where r and theta and z are related to x, y, and z by the equations x is equal to r cosine of theta, y is equal to r sine of theta, and z is equal to z. So really r and theta are the polar coordinates of our point if we were to project it onto the xy plane, and then the z coordinate is just the normal rectangular z coordinate. So let's consider how we would convert a triple integral to an integral in terms of cylindrical coordinates. So the following theorem will give us a way to evaluate triple integrals using cylindrical coordinates. So here's what it says. If we have a function f, which is continuous over a type 1 region, E, which could be described as the set of all points x, y, z in space, and if this is a type 1 region, that means we're thinking about this in terms of being bounded above and below in the z direction by two functions h1 and h2 of x and y. So it's bounded above and below by the graphs of two surfaces, where xy lies in some plane region D, where D is the projection of our solid region onto the xy plane. Now let's suppose here that plane region D can be easily described using polar coordinates. Maybe it's a disk or some cardioid-shaped region or an annulus or part of a disk. So let's suppose D here is given by the set of polar coordinates r theta, where theta ranges between alpha and beta, and r is bounded above and below by two functions of theta, maybe constant values or maybe functions of theta if we're talking about a cardioid-shaped region. So in order to evaluate the triple integral of our function f over that solid region E, we would use an iterated integral, which is making use of cylindrical coordinates. So first, we would change our integrand from a function of x, y, and z to a function of the cylindrical coordinates. So x is replaced by r cosine theta, y by r sine theta, and then z is the z coordinate for cylindrical coordinates. Our limits of integration for our innermost integral, that is with respect to z, well, z, we said here, was bounded above and below by functions h1 and h2 of x and y. So we now replace those functions of x and y by the polar coordinates. So here our x and y values are again r cosine theta and r sine of theta. And then once we evaluate that innermost integral, we're then evaluating the double integral of that function over our projection d. So here, the outer two integrals, expressing that double integral as an iterated integral, we would next integrate with respect to r, and the bounds on r were from g1 to g2 of theta. And then with respect to theta, where theta was ranging from alpha to beta here. And then the differential of area for that outer double integral, remember in polar coordinates, is given by r times dr d theta. So here we pick up an extra factor of r from that outer double integral in terms of polar coordinates, the same way that we saw that in our earlier section. So now that we have this, let's look at an example where we might make use of triple integral in cylindrical coordinates. So in this next example, we're asked to evaluate the given triple integral, and we're told to try to evaluate this by converting to cylindrical coordinates. So if we were to try to evaluate this directly as an iterated integral, what we see are limits of integration in terms of x and y are quite messy. So this would be a pretty nasty triple integral to evaluate directly. But let's see if we can visualize the region that this iterated integral is describing and see if we could more easily describe it in terms of cylindrical coordinates. So in this one, let's start by looking at our inner integral. The inner one with respect to z has a lower bound of x squared plus y squared. So that is the circular paraboloid, which is opening upward from the xy plane. The cross sections are circles. And our upper bound is 2 minus x squared minus y squared, which is a circular paraboloid opening downward. It has its vertex at 0, 0, 2, and it's opening downward. So we see that these two paraboloids are going to intersect each other in a circle. So let's see if we could find the equation of that circle. So to find a circle of intersection, we would set our two values of z equal to each other. That would be 2 minus x squared minus y squared is equal to x squared plus y squared. So we find that 2 is equal to 2 times x squared plus y squared. So x squared plus y squared is equal to 1. So here we have this circle of intersection for those two circular paraboloids is the circle x squared plus y squared equals 1. Now, if we were to take this solid region and project it onto the xy plane, let's see what our plane region of integration would be for the outer double integral. So here, if we project this solid onto the xy plane, we get a disk of radius 1. That is x squared plus y squared is less than or equal to 1. And let's see if we want to integrate over that entire disk. So if we visualize this disk in the xy plane, its outer edge is this circle of radius 1. And let's call our region D. Now here, looking at our limits of integration for y and z, well, with respect to y, we're being bounded above and below by the positive or negative square root of 1 minus x squared. So that's referring to the lower half of the circle for the negative square root value and the upper half circle. And then our x values are allowed to range from -1 to +1. So here, our region of integration in the xy plane is the entire disk, everything from the bottom half circle to the top half circle on the x interval from -1 to 1. So once we have this visualization, let's see if we can describe this region more easily using cylindrical coordinates. So here we see that our plane region D could be, since it's a disk, could be pretty easily described in terms of polar coordinates. So let's maybe try to express this in terms of cylindrical coordinates. So here, our outermost integral with respect to theta, if we're using cylindrical coordinates, would range from 0 to 2 pi, since we're integrating over the full disk, a full 360-degree rotation or 2 pi radian rotation. Our value for r, the next integral, well, for this disk, r could range from 0, that is the center of the disk, out to the outer circle, which was a circle of radius 1. And then our innermost integral with respect to z, well, our bounds on z, we had a lower bound of x squared plus y squared, which in terms of cylindrical coordinates is r squared. And then the upper bound, 2 minus x squared minus y squared, becomes 2 minus r squared. Now the integrand that we're left with, the square root of x squared plus y squared, that is the square root of r squared, or just r. And then changing our differential to polar coordinates, remember we pick up an extra factor of r. So we're going to have times another factor of r, and then we're integrating in the order dz, dr, d theta. So here our inner function is r squared. We're integrating with respect to z, so it's a constant. So let's see what we have here. So we have our outer integral from 0 to 2 pi, and then from 0 to 1. We had an r squared times the antiderivative with respect to z would give us z. So when we evaluate at the upper limit, we have 2 minus r squared, and then we subtract what we get when we plug in the lower limit for z, which would be r squared. And then integrating with respect to r and theta. So let's simplify a little bit here. We now have the integral from 0 to 2 pi and from 0 to 1. Grouping like terms and distributing the r squared, we have 2r squared minus 2r to the fourth dr d theta. So now we can use our sort of shortcut technique here. Notice that our innermost integral with respect to r is constant with respect to theta. So if I were to pull that inner integral with respect to r out in front of my theta integral, then I would be left with the integral from 0 to 2 pi of d theta, which is just 2 pi. So we have a constant 2 pi out in front times the integral from 0 to 1 of 2r squared minus 2r to the fourth dr. So we now have 2 pi times our antiderivative would be 2/3 r cubed minus 2/5 r to the fifth, evaluating from 0 to 1. So we're left with 2 pi times 2/3 minus 2/5 when we plug in 1 for r. And so we're left with a total of 8 pi over 15, getting a common denominator here. So we see that by visualizing the region that was described by this given iterated integral in terms of rectangular coordinates, we could express that same integral in terms of cylindrical coordinates, and we get a function which is much easier to handle. So let's look at another example. In our next one, we're asked to evaluate the triple integral of the square root of x squared plus y squared over the solid region E, which we're told is the region bounded by the paraboloid. Z is 9 minus x squared minus y squared, and the xy plane, which is the plane z equals 0. So let's start by visualizing our region of integration here. So we're being bounded by two functions of x and y, so two surfaces. One surface is this paraboloid, 9 minus x squared minus y squared, which is a paraboloid whose vertex is at 0, 0, 9. And it's circular paraboloid opening downward. And it intersects the xy plane, which is the plane z equals 0. And here, their intersection would be a circle, since this is a circular paraboloid. We could also see that by setting these two values for z equal to each other. We would take 9 minus x squared minus y squared, set it to 0, and we find x squared plus y squared would be equal to 9. So this curve of intersection in the xy plane is the circle centered at the origin of radius 3. So if we were to project our solid region E down onto the xy plane, we get a disk. So here our projection onto the xy plane gives us this disk of radius 3 centered at the origin. So let's see how we could set up our triple integral in terms of cylindrical coordinates. Let's see if we can describe this region. So here our region E could be described in terms of cylindrical coordinates, r, theta, and z, where our range of theta values is from 0 to 2 pi, since we're integrating in the plane over the full disk D. Our range of r values would be from 0 to 3, since it was a disk of radius 3. And then our range of z values, well, z could be ranging from the xy plane, z equals 0, up to the equation for our paraboloid, 9 minus x squared minus y squared. So here 9 minus r squared in terms of spherical coordinates. So let's see if we could set up our iterated integral from here. So here, the integral over E of the square root of x squared plus y squared dv can be expressed as an iterated integral, where theta goes from 0 to 2 pi, r goes from 0 to 3, and z goes from 0 to 9 minus r squared. The function that we're integrating is the square root of x squared plus y squared, which reduces to r. And then the order that we're integrating in is dz, and then r dr d theta. So we're going to get an r squared dr d theta when we pick up that extra factor of r for making the change to cylindrical coordinates. So let's see what we have here. So starting with our innermost integral with respect to z, let's see what we have for our antiderivative. So we're left with the double integral, 0 to 2 pi, 0 to 3. We have an r squared times integrating with respect to z, we would have a z. And evaluating at the upper limit, we get 9 minus r squared minus what we get when we plug in 0, which is 0. So r squared times 9 minus r squared, and then dr d theta. Now here we can already see that this inner integral with respect to r does not depend on theta. After I evaluate it, it will be constant. So I could evaluate my outer integral first, and I get a constant 2 pi times the integral from 0 to 3 of distributing our r squared. We have 9 r squared minus r to the 4th dr. So we have then 2 pi times our antiderivative with respect to r is 3r cubed minus 1 over 5 r to the 5th, evaluated from 0 to 3. So that gives us a 2 pi times, plugging in 3 for r, we have 3 cubed times 3, so 3 to the 4th, which would be 81, minus 3 to the 5th, so 243 over 5. And then we subtract what we get when we plug in 0, which is 0 here. So we are left with, after some simplification, 324 pi over 5. All right. So here, again, making this change to cylindrical coordinates gives us functions which are much easier to integrate than the ones we would have if we left this expressed in terms of the rectangular coordinates x, y, and z. Let's move on to the next part of our section. Let's suppose that we are integrating a triple integral over a solid region, which is maybe part of a sphere, or if we want to integrate over a sphere of a given radius. So spheres are not as easily described in terms of rectangular or cylindrical coordinates, but they do have easy descriptions in terms of spherical coordinates. So we had seen earlier in the course, these spherical coordinates would be useful in describing surfaces which are spheres, parts of spheres, cones, regions involving cones have pretty simple descriptions in terms of spherical coordinates. So let's recall the spherical coordinates for a point in space. They're represented as the ordered triple rho, theta, phi, and the relation between rho, theta, and phi to x, y, and z are given by the conversion formulas. X is equal to rho sine of phi cosine theta. Y is equal to rho sine of phi sine of theta. And z is equal to rho times cosine of phi. And let's recall what these different coordinates represent. So for a point in space, we have our standard rectangular coordinate system defined by the x, y, and z axes. So we could have some point, P, in space represented by this ordered triple rho, theta, and phi. So let's recall what these values represent. So here, rho, our first value, is the distance from our point to the origin. So if I were to extend a line segment from the origin to my point, the length of that line segment is what we call rho. Theta is the same as the polar coordinate value of theta. So if we were to think about projecting our point onto the xy plane, theta is the angle that would be formed from the positive x-axis, moving counterclockwise to get to the line segment which connects the origin to the projection of our point in the xy plane. And our last value for spherical coordinates, phi, is the angle measure from the positive z-axis downward to the line which connects the origin to my point. So it's a measure of how far we're rotating downward from the z-axis. So now that we've recalled what these spherical coordinates represent, let's think about how we could transform a integral over a region to an integral using spherical coordinates. So we have the following theorem to accomplish that. This is a formula for triple integrals making use of spherical coordinates. So it says if we have a continuous function f on some bounded region E, which is given in spherical coordinates by the set of all points r theta phi, rho theta phi, such that rho ranges from A to B, theta ranges from alpha to beta, and phi ranges from gamma to delta. So if these are all between constant values, then we can set up the iterated integral for our triple integral of the function f over the region E as follows. So first we would transform our function to spherical coordinates. So x is replaced by rho sine of phi cosine theta. Y is replaced by rho sine phi sine theta. And z is replaced by rho cosine of phi. And then we're going to integrate this in the order d rho, d theta, d phi, where our inner integral with respect to rho had values that ranged from a to b. The next integral with respect to theta was ranging from alpha to beta. And then with respect to phi for the outermost was ranging from gamma to delta. Now notice that we pick up this extra factor of rho squared times sine of phi on the end. So the reason for this extra factor is that the volume of a solid rectangular region given in terms of the spherical coordinates would be rho squared sine phi times d rho d phi d theta. So just like we had the area of a region described in the plane in terms of polar coordinates as given by r dr d theta, for spherical coordinates we pick up this extra factor that's accounting for the volume expressed in terms of spherical coordinates. It's given by rho squared sine phi. So we have got to remember that extra factor that we pick up there. So let's look at an example of evaluating a triple integral using spherical coordinates. It seems like this is a messy way to express a function, so why would we want to do this? So in this next example, we have a triple integral of x e to the x squared plus y squared plus z squared quantity squared, and we're integrating over the portion of the unit ball. So that is the solid region inside the unit sphere. And we want just the portion of that unit ball which lies in the first octant. So let's see if we could visualize that region. And so our first octant is described by the positive x, y, and z axes. And we're looking at the part of the unit ball which lies in this octant. So visualizing this, well, it's the sphere, or its boundary is the sphere of radius 1. So we have this ball, which is cut off in the first octant as a region that looks like this. Its intercepts are at 1. And we see that we could describe this region pretty easily in terms of spherical coordinates. For any sphere or part of a sphere, we've got a pretty easy description. So let's see how we could describe this region E using those spherical coordinates. It'd be the set of points rho, theta, phi, such that the values of rho could range from 0, that is the origin, out to the edge of this ball, which was radius 1. So rho would range from 0 to 1. Our value for theta could range from 0, so that is points along the positive x-axis, or we are then rotating up to the positive y-axis, which would be a pi over 2 radian rotation. So here, theta could range from 0 to 90 degrees, or pi over 2 radians. And then our last value, phi, is this angle measured from the positive z-axis downward. And we see we could go from the positive z-axis to the positive y or x-axes. So we could range for phi from 0 to pi over 2, another 90 degree or pi over 2 radian value for phi. So let's see if we can then express this triple integral as an iterated integral using spherical coordinates. So here, the triple integral over e of x times e to the x squared plus y squared plus z squared, quantity squared, dv, can be expressed as the following iterated integral. So we would have our range of phi values for the outermost integral from 0 to pi over 2. For the next integral with respect to theta, we have a range from 0 to pi over 2 as well. And then for the innermost integral with respect to rho, we had a range from 0 to 1. Now here our integrand was x. So in terms of spherical coordinates, x is given by rho sine of phi cosine of theta times e raised to the x squared plus y squared plus z squared quantity squared. Now recall that the sum of x, y, and z squared for spherical coordinates is rho squared. So we have rho squared squared, or rho to the 4th power for our exponent in that function. And then on the end, we had the differential of volume, dv, which using spherical coordinates, we pick up an extra factor of rho squared sine of phi. And here we were integrating in the order d rho, d theta, d phi. So let's see if we could evaluate this. Let's start by maybe cleaning up our integrand by combining some like terms. So here we had outer integral from 0 to pi over 2, and 0 to pi over 2, and 0 to 1. Now if we group all of our rho terms together, we have rho squared times rho times e raised to the rho to the 4th power. So all together we have rho cubed e raised to the rho to the 4th. Then grouping our phi terms, well, we had a sine of phi times another sine of phi. So we have sine squared phi. And then the only theta term that we had was cosine of theta. And then integrating here, d rho, d phi, d theta, d phi. So we could start by integrating our innermost function with respect to theta, working our way outwards. Or we can make use of our little shortcut technique here by thinking about maybe pulling our interior integrals out in front of the outer ones. So what I mean by that is our inner integral here is with respect to rho. The only terms that depend on rho are these first two, and then we're evaluating from 0 to 1. So when I integrate this with respect to rho and plug in 0 and 1 and take my difference, I'm left with a constant with respect to theta and phi. So this innermost integral, we can pull out in front of the other two integrals. So I have the integral from 0 to 1 of rho cubed times e raised to the rho to the fourth power, and my differential d rho I can pull out in front of the other two integrals. Now what I'm left with then is an integral where the next variable of integration is with respect to theta, and here the only term involving theta is cosine theta, which I would then evaluate from 0 to pi over 2, and I would have a constant with respect to that last variable phi. So if I pull that term out in front of the phi integral, I would have the integral from 0 to pi over 2 of cosine theta d theta. And then the integral which I'm left with, since I pulled everything else out in front of this one, is the integral from 0 to pi over 2 of my sine squared of phi d phi. And then here we can see what we're left with is just the product of these individual integrals with respect to each variable. So in the case that our limits of integration for all three variables are constants, we can think about this as a product since none of our limits of integration were functions of the other variables. So let's evaluate this. To evaluate our first integral, rho cubed times e rho to the fourth, we're going to make use of a substitution, so a little scratch work on the side. We're going to let u equal rho to the fourth, so that du is 4 rho cubed d rho. So solving for d rho, we have a du over 4 rho cubed. So that gives us a leftover factor of 1/4. This becomes e to the u du. And our limits of integration were 0 and 1. Now when rho is equal to 0, u is 0. And when rho is 1, u is also 1. Now for our next integral, we can evaluate this one directly. The antiderivative of cosine of theta is sine of theta. And we're then evaluating from 0 to pi over 2. And our last term, to integrate sine squared of theta, we have to make use of our trig identity. So we're going to rewrite this as the integral from 0 to pi over 2 of 1 minus cosine of 2 phi all over 2 d phi here. So let's see what we have. We have for the antiderivative of this first term a 1/4 e to the u, which is being evaluated from 0 to 1. This middle term, we had sine of theta, so evaluating it at pi over 2, sine of pi over 2 is 1, minus sine of 0 is 0. And then the antiderivative for this last term, well, the constant 1/2 integrated with respect to phi gives us phi over 2, minus the antiderivative of half of cosine of 2 phi becomes 1/4 sine of 2 phi, which is being evaluated from 0 to pi over 2. So let's see what we're left with. This first term, we have a 1/4 times, when we plug in 1 for u, we have e to the first minus e to the 0 is 1. Our middle term here was 1 minus 0, so we're just multiplying by 1. And then our last term, plugging in pi over 2 for phi, we have pi over 4, minus 1/4 times sine of pi, which is 0, and then subtracting what we get when we plug in 0, we have 0. So altogether, if I pull my constant pi over 4 out in front, I have pi over 16 times e minus 1. So this would be the value of that triple integral over this portion of the ball. So we see that this is a little bit tedious, but this is much easier than trying to find an antiderivative of this function in terms of rectangular coordinates and trying to describe this part of the ball using rectangular coordinates x, y, and z. So for our last example, let's look at another one of these. So here we are given an iterated integral in terms of rectangular coordinates x, y, and z, and we're told to evaluate it by converting to spherical coordinates. So we first need to visualize the region that's being described by this iterated integral. So let's start by looking at our innermost integral with respect to z. Z is being bounded below by 0, so that is the xy plane, and above by the square root of 9 minus x squared minus y squared. So that represents the upper hemisphere of a sphere of radius 3. Let's see why exactly that's the case. We're looking at the surface defined as z equals the square root of 9 minus x squared minus y squared. So squaring both sides, we have z squared is 9 minus x squared minus y squared. So the sum of the squares would be equal to 9. So we recognize that as the equation of a sphere centered at the origin of radius 3. And here, since z was being described as the positive square root of that value, that means we're only considering positive values for z. So here we're just working with the upper hemisphere. So here, upper half sphere, which lies above the xy plane, since z was being bounded below by 0, of radius 3. So it intersects the xy plane in a circle. If we set z equal to 0 in the equation for that sphere, we have x squared plus y squared is equal to 9 for the circle describing this outer edge of our solid E. Now the projection of this onto the xy plane gives us a disk. And let's think about if we're integrating over that entire disk here. So here, let's maybe use a different color for our plane region. So looking at that disk in the xy plane, its boundary is the circle of radius 3. And we asked, do we want to integrate over the full disk? So moving to our outer integrals with respect to y and x, we see y ranges from the negative square root of 9 minus x squared to positive square root of 9 minus x squared. So maybe let me use red here. That describes our upper half circle and lower half circle of radius 3. And then our x values are ranging from -3 to +3. So we are integrating over the full disk. Let's call that disk D for now. So in this example, let's see if we could describe E in terms of the spherical coordinate system. So here we would have the set of all points whose coordinates are rho, theta, phi, where rho, the radius of my sphere, could range from 0 to 3. Theta, which would be the angle revolved from the positive x-axis when we look at our projection onto the xy plane would go from 0 to 2 pi, since we're talking about the entire disk. And phi would be the angle measure from the positive z-axis. So from our positive z-axis, for the upper half of a sphere, we could rotate down to the xy plane. So here phi could range from 0 to pi over 2. So let's see if we can convert this iterated integral to an integral in terms of spherical coordinates. So here, I don't want to rewrite this full integral, but let's say this is equal to, starting with our outermost integral, in terms of phi, we would have from 0 to pi over 2. The next integral with respect to theta would range from 0 to 2 pi. And then the innermost would be with respect to rho from 0 to 3. And the function that we are integrating here was given by z. Now z in terms of the spherical coordinate system is given by rho times cosine of phi, and then times the square root of the sum of x, y, and z squared, which would be rho squared. Taking our square root, we have rho. And then changing the differential of volume from rectangular coordinates dz, dy, dx to polar coordinates. Recall that we pick up an extra factor of rho squared sine of phi. And then we're integrating here in the order d rho, d theta, d phi. So grouping some like terms, let's see what we have. We've got the integral from 0 to pi over 2, 0 to 2 pi, and 0 to 3. So grouping our rho terms together, we have altogether rho to the 4th. There are no theta terms in here. And then grouping our phi terms, we had a sine of phi times cosine of phi. Here, d rho, d theta, d phi. So as with our previous example, we see that the limits of integration for all three of our variables are constants. So I can pull my inner integrals outside of the outer double integral. So my inner integral with respect to phi was from 0 to 3, or with respect to rho was from 0 to 3, rho to the 4th, d rho. And then I'm left with the double integral with respect to theta and phi. But because theta is constant, or the integral of this function with respect to theta is constant, I can pull it out in front of the phi integral, and I'm left with the integral from 0 to 2 pi of 1 d theta times, for the integral that I'm left with, after I pull out my interior integrals, I have the integral from 0 to pi over 2 of sine phi cosine phi d phi. So evaluating this first antiderivative, we have 1/5 rho to the 5th from 0 to 3. Integrating the constant function 1 with respect to theta from 0 to 2 pi, we get 2 pi minus 0, or just 2 pi. And evaluating this last antiderivative, we're going to make use of a substitution. So we would let u equal to sine of phi, so that du is cosine phi d phi. So changing our limits of integration, when phi is equal to 0, u is sine of 0, which is still 0. And when phi is pi over 2, u is sine of pi over 2, which is 1. And our integrand is now given by u du. So evaluating this first term, when we plug in 3 for rho, we have 3 to the 5th, or 243 over 5, times, this middle term was 2 pi. And then the antiderivative of this last term is 1/2 u squared, evaluating from 0 to 1. So let's see what we're left with. We have our 243 over 5 times 2 pi times, plugging in 1 for u, we have 1/2, minus plugging in 0 gives us 0. So our 2 pi times 1/2 is just pi, times the 243 over 5. So 243 pi all over 5. So again, in this last example, we see by converting to spherical coordinates, we get a triple integral, or an iterated integral, which is much easier to evaluate than the one that was given.